Comes on everyone, let's start off. Last thing that we did was X-rays. Hope everyone has gone through the notes and hope you all started solving. So we are left out with the nuclear physics. Again, it's mostly theoretical, important, but theoretical, and let's see, it has a lot to do with numbers. Great. Nuclear physics. So primarily we're going to study more about the nucleus. Till now we dealt with an atomic level. So basically we saw interaction between electrons between two molecules and everything. So whenever two atoms collided, the loss in energy went into electrons for excitation and everything. So this is something even more fundamental. We are going inside the nucleus. So AXZ, this thing I already used it before. So this is the representation of an element. A is your atomic mass. Which is also number of neutrons plus protons. That is your atomic number, which is number of protons. Others, keep your hands on. Size and density of the nucleus. So the radius of the nucleus is given by r is equal to r naught e power 1 by 3. Remember, this is not the radius of the atom. We are talking about radius of the nucleus. R naught value is around 1.4 into 10 power minus 15 meters. There, this is your first formula in this. They do ask questions based on this. So there was one question like this. Find ratio of radius of aluminum and copper nucleus. If you remember, copper mass is around 64, 63 point something, but round it off, and aluminum is around 27. So if you take the ratio here, you'll get R of aluminum by R of copper. That would be 27 by 64 whole power 1 by 3, which is 3 by 4. So easy questions, but if you don't know the formula and all, you'll be gone. And if you look at the properties of this, the size of the nucleus is very small. Is around 10 power minus 15 meters. And whereas the size of the atom is around 10 power So if you look at the radius of the first orbit of hydrogen, 0.53 angstroms, it is in the range of 10 power minus 10. Nucleus is in Fermi range, so 10 power minus 15 meter is 1 Fermi. So meaning just to see how small it is, think of like this. If you take a basketball, right? If you take a basketball, let's say that is the nucleus. You'll find the first electron 1 kilometer from there. That's the size of the atom. So atom would be like 1 kilometer radius circle, and your nucleus is like a basketball at the center. So it is so small. It's 10 power 5 times, bigger the atom. And next thing, if you look at the density of the nucleus in the center is almost constant. That is because whether you take uranium or sodium, all are made of protons and neutrons only. They're made of the same stuff. And near the surface, it decreases. This is mostly due to the packing. At the center, this due to nuclear forces, everything is tightly packed. On the edges, they don't have that kind of a packing. So near the surface, the density decreases. The average density is independent of atomic number, meaning you take uranium or you take sodium or you take helium, the average density is same. It's like saying if you take 1 kg iron or 10,000 kg iron or 1 ton of iron, it is the same thing, independent of atomic number, because fundamentally everything is made of the same nucleus. The average density comes to around 1.4 into 10 power 17 kgs per meter cube. Huge number. Clear with that? That's some properties of this. Next thing. There's a lot of theory. So listen carefully. The most important thing is the terminologies and your basic formulas. We do have one or two things which are important for an advanced perspective. So these masses are so small, measuring them in terms of kgs and grams doesn't make sense. So we use something called atomic mass unit. AMU. So the definition of AMU, so whenever you see the masses, sodium 23, Na11, this 23 is actually the atomic mass unit. So one AMU is defined as 1/12 of a carbon mass. The value turns out to be around 1.66 into 10 power minus 27 kgs. Next time now, when you see any atomic mass of any nothing, we're going to see later on, you'll observe, for example, if you take iron, it is around 56.9 something, something, something. You will see oxygen also, it will be like 16 point something, something, something. There will be always some decimals. Only for carbon, you will see exactly 12C6, perfect 12. Because that is the definition of AMU, isn't it? 1/12 of whatever is the carbon mass is one AMU. The only carbon will have a perfect number 12. Everything else, the numbers will keep changing. You will get always fractions, and decimals. Then energy mass equivalence. So if you think about mass, fundamentally mass is nothing but a highly concentrated form of energy. Mass is a highly condensed form of energy. Till now, we never had a problem with this. We always studied mass separately and energy separately. We can't do that anymore because when you go to the size of a nucleus, we will observe sometimes mass becomes energy and energy becomes mass. So law of conservation of energy and law of conservation of mass both will fail. But law of energy plus mass conservation is always valid. So you're getting it. So your regular conservations won't work anymore. Momentum works, angular momentum still works. Law of conservation of energy doesn't work. Law of conservation of mass doesn't work. So we write something new. We call it law of energy plus mass conservation. So E is equal to mc square. This is the equation we use. For example, if you take 1 kg, and if you make this into pure energy, this turns out to around E is equal to mc square. That is 9 into 10 power 16 joules. That's a huge number. How big is that number? If you look at the total consumption of India, right? I think we consume around 10 gigawatts. 10 gigawatts, that is, giga is 10 power 9. 1 watt is joule per second, means every second, again, approximately the entire country is consuming this much energy every second at this point of time. And if you have this much energy, 9 into 10 power 16 divided by 10 power 10, that comes to around 9 into 10 power 6 seconds. In a day, you have around 86,400 seconds. Let's make it 90,000 for convenience. 9 goes off. and that would be 9 by 10 power 4, that is. That will be around 10 power 2 days or 100 days. You know the meaning of this? If you can actually convert 1 kg of mass into pure energy, and if you can convert that into electricity, you can run the entire country for 100 days. I have taken it as 10 gigawatts. If it is 30 gigawatts, that is extreme case. Even then, you can run the country for a month. That much energy you get if you actually convert 1 kg into energy. So during a nuclear bomb explosion, right, around 50 to 60 grams of mass gets converted into energy. That's it, 50 grams, and that is sufficient to wipe out a city. So these nuclear reactions, right, they produce immense amount of energy. We can't even compare. If you look at a nuclear power plant, they do the refueling once in 2 years. That thing is just producing power non-stop for 2 years without refueling. Yeah, the other side effects, the radioactivity and everything, but in terms of energy, nothing beats, nuclear reactions. So 1 AMU will be, so if you convert 1 AMU mass into energy, this is 931.5 million electron volt. This is a number which you should remember. Means if you convert this much mass, 1.66 into 10 power minus 27 kgs, you get 931.5 million electron volts. MeV is million electron volts. We did discuss this last time. That is a number you need to remember. So in nuclear reactions, this was a CT equation. Which of the following is not conserved in nuclear reaction? There is a statement like that. In nuclear reactions, energy plus mass is conserved. So mass is also a type of energy. In mechanics, we never had that issue. Mass never becomes energy in normal situations. So only energy or mass is not conserved. Next thing. Now in school, we also studied, when you take a sodium atom or a calcium atom, there are like 20 protons inside. And we also studied in school, protons, like charge particles, will repel, isn't it? But ever thought about this? If like charge particles are repelling and protons should repel each other, you're taking 20 protons and keeping it in such a small nucleus. Shouldn't the protons just, repel each other and fly off? Technically, that should have happened, but that is not happening. So this is how you always think, this is what should have happened, but this didn't happen. I mean, there's something else that is happening there. It's like, for example, let's say you and your sister are there in the house, right? Mom has brought, 2 cakes for both of you. She kept it in the refrigerator and went out. When she came back, both the cakes are missing. You know you didn't eat the cakes. Who ate the cakes? See, you're getting at what is happening. You don't have a proof that someone ate the cake, but you know who ate the cake. It is always like that. You always go with a counter argument. This is something should have happened because protons are like charged particles, positive. They should have repelled and flown off, but they're still there. That means someone else is keeping them together. So people started thinking about this, and they figured out these protons and neutrons, they have something called a nuclear force. That is how always a theory starts. You start with the theory, there is a nuclear force, and then you try to find out whether it exists. So these are the forces between the nucleons. Recently in my house, so my mom was brought something. She was stitching some small clothes or something. One of the cloth was missing. So my mom thought maybe she forgot somewhere. Then next day there was one banana missing. Right? My mom started thinking there might be a ghost in the house. Right? And my dad's argument was it must be a rat. They both started fighting. It is a rat or a ghost. So and I don't think it's still resolved. For now they're on a break. So Rat is having fun for now. So people come up with conclusions, right? That's how you make a theory, first of all. And now you have to prove it. My dad is, I think he's going to buy a rat ka thing and he's going to catch the rat and prove my dad it is a rat and not a ghost. And my mom has no way to catch a ghost and prove it is a ghost. So if they do catch one, both of them will run away from the house. So I'm not sure how this is going to work, but happens, huh? When your parents start becoming old, they start behaving like kids. So this is what they noticed. If you take two neutrons, the force between them is same force as neutron and proton, and the force between proton and proton. So even this proton and proton actually attract each other due to nuclear force. So these nuclear forces is independent of charge. It doesn't depend on the charge. Again, we don't have a perfect explanation so far, but again, we have a theory which is explaining so far. So this, when you go to the nucleus level, right, we actually have a lot of unknowns. Nuclear force is independent of charge and it is always attractive. So the attractive force, nuclear force between neutron, proton, and proton, proton is same. The reason why we don't see this in normal thing is this is a very short range. Around 1 Fermi, which is 10 power minus 15 meters. So only when you're in this range, you can actually see a nuclear force. So that means when you take a proton and a proton, when you keep them far, they repel each other. As you bring them closer and closer and closer, at some point, 1 Fermi distance, suddenly they start attracting each other. Both the protons will just stick. So this is what is actually happening right now. When you're touching the table in front of you, you think you're touching the table, you're not touching it. If you actually touch the table, the nucleus on your hand and the nucleus on the table will fuse. There'll be nuclear fusion and there'll be a blast and everything just explodes. You create a nuclear bomb basically. Right. So when you're touching something, what you're experiencing right now, the table you're touching, the thing you're experiencing is actually electrostatic repulsion between the molecules between your hand and the molecules on the table. This we discussed, in NLM, if you remember. So the theory so far we have is if you have a neutron, we have a proton, this nuclear force will come into picture only when you're, touching the other one or very close to it. That means if you see this neutron and this proton do not have nuclear force. So only the immediate neighbor you'll be able to interact. And people came with a theory called an exchange theory. So the theory goes like this. Imagine, right, you're watching two people playing tennis, right, from very far, maybe some 300, 400 meters from top of a building, you're watching two people playing tennis. And let's imagine you don't know what is a tennis game, right? And there are two people there, one A and B. Now, since you're looking from a height of 300, 400 meters, you won't be able to see the ball. And these two people will look like two small dots. When you observe them, this is what you'll notice. A is going here, B will come here. A comes here, B goes here. A goes here, B goes here. So they're just moving around. When you look at A and B, right, it doesn't make any sense. Like, why the hell these two people are running around, what they're doing. You don't understand, but you know inherently, right, something is happening, right? Whenever A moves, immediately B moves. Then B is moving, so A is moving. But when you're looking from a height of 200, 300 meters, you don't understand why they're moving like that. But as you keep getting closer and closer and closer, you will notice there is a ball between them. A is hitting the ball, B is running there to hit the ball again, and the ball is bouncing between them. So even though A and B are not, attached to each other with anything, but they're moving in sync because of that one ball which is bouncing between them. Making sense? So A and B are two independent people, but both the motions are getting constrained because of that particle or the ball which is bouncing between them. Same way, these neutrons or nucleons, right? They exchange particles like muons, bosons, there are a lot of things. We'll not get into that. They keep exchanging these particles. Because of that particles, they generate a nuclear force. That is a theory so far that is accepted. So only nucleons in the immediate surrounding. Meaning if you go distance of, if you put a neutron, proton, and neutron, gone. These two will not interact only. Only this N and P will interact. So it is such a short range force. in the immediate region, exchange particles. Generating nuclear forces. A lot of stuff is unknown after that. Like these forces are called exchange forces because you're exchanging particles, and that is what is keeping together. And that is the reason you need to be very short range in order for this to happen. Once you exceed one Fermi, the force just goes off, it vanishes. There is no force between them. Electrostatic force will dominate. So if you look at the ratio of the forces, gravity, let's say if you take two protons and if you see the gravitational force between them, electrostatic and the nuclear force, the ratio is 1:2. Electrostatic is 10 power 36. Nuclear is 10 power 38. Huge. Electrostatic is pretty huge compared to gravity. And if you see the nuclear force, it is almost 100 times stronger than electrostatic. That is the reason when you bring two protons very close, more than the repulsion, the attraction dominates. And that is the reason inside a calcium, the protons don't fly away. Now here they can pop up a theoretical question. If they ask you, arrange the net force between neutron, 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 proton, proton, proton. Now see, the nuclear force, all three are equal. But if they ask you for the net force, a neutron, neutron will have no repulsion. Neutron, proton also will have no repulsion. So they're actually equal. But when you take a proton, proton, they'll have nuclear force plus also a slight electrostatic repulsion, isn't it? So the overall force will decrease. So a proton-proton net force is slightly smaller than neutron-neutron or neutron-proton. This is due to that repulsion. So be careful what they're asking. Are they asking the nuclear force? Then they're all equal. If they're asking net force, then they're not equal. So due to electrostatic repulsion, the force slightly decreases. Clear with that? Now what happens with the stability of the nucleus? So now we established the fact there is something called a nuclear force. So when you take something like hydrogen, there is only one proton, there's nothing to interact. But when you take, as the size increases, stability actually starts increasing. It's kind of like this, let's say if you're just staying alone every time, no friends, nothing, right? No one to talk to, no one to care of you. You are just gone, matlab isolated, right? You're kind of like, feels very horrible. But let's say if you have maybe one person, suddenly stability increases. So if you have a proton and a neutron is more stable than a regular hydrogen. But let's say if you have a family, your friends and everything, group of 10, 15 people, suddenly your life becomes more comfortable. But imagine you have 100 relatives who keeps coming every day. Every relative comes to your house every day, one after another, one after another. Next day, another relative. It feels miserable. Like, what the hell are these relatives doing? Ever happened to you? Relatives are just coming every day, morning, evening, morning, evening. You will notice this not now. After once you go to engineering, right? You come home for vacation. If you're joining an IIT, BITS or NITs or anywhere, you come home for vacation after 4 months. The first thing you will do, first 10 days, you're just going to every relative's house everywhere. Your seniors tell me that only. Sir, they gave us 3 months holidays. We didn't know what to do. So 1 month I was roaming around to all relatives' house. It's like, Zoom, when you get a new animal, they show everywhere, na? It's kind of like that. So you're just roaming everywhere. So once you have a bunch of, protons and neutrons, a bunch, the stability actually bumps up a lot. So there is more interaction. So there is a more nuclear force. So this thing gets more packed and there is more stability. Now the problem occurs when the size becomes too big. When the size keeps going bigger and bigger, for example, you take uranium, 238 nucleons, in that there are 92 protons. Now look at the problem here. if you look at the proton on the edge, no matter how big it is, now think about the proton on the edge. It will be surrounded by maybe 3 or 4 of them, isn't it? So maybe I can put a little more. So if I pack it properly, something like this. Can you see the problem there? If you look at the protons on the edge, we have a problem. You can interact with only maximum 3 or 4 at a time. But every proton in the nucleus, if you take uranium, there are another 91 protons. Every other nucleus proton here is going to repel it. Now, can you see what is the problem there? Agree, nuclear force is strong, but when 90 protons are pushing you out, what will happen? The electrostatic force will start getting pretty close to the nuclear force value, isn't it? And how many people are keeping you together? Only 4 or 5 people. So once the size of the nucleus becomes pretty big, right, these protons in the entire nucleus will start pushing this one proton on the edges. So the atom is pretty unstable on the edges. All you need is a small disturbance and this piece will break off and come out. So when it breaks off, what do you get out? If you see, you'll get an alpha particle out. Because the helium nucleus is more stable, we'll see later on. So that is the reason you get an alpha emission. Because the nucleus becomes unstable. As the size becomes more, the edges become pretty unstable. Even if you have a small disturbance, suddenly, right, the edges will start breaking off and you start emitting alpha particles and other particles. This is what leads to instability. That means you're too small, we have a problem, you're not stable. If you're too big, it also creates an instability. So there's an optimal size somewhere in the middle. This is the reason why you get a radioactive decay. The nucleus is becoming unstable. Is that making sense? The explanation is making kind of little sense. Because edges may only 4 or 5 people are attracting you, but like there are 90-95 protons which are pushing you out. The nuclear force, electrostatic force will start dominating. As size increases, nuclear force increases. Therefore, stability increases. So there is a psychological fact, humans, at any point of time, you can only keep a proper interaction with around 5 people. 5 people roughly. The moment the sixth person comes, in that 5, someone else will keep, losing that thing. When you want to, keep a relation with someone, you need to spend time. Right? Your mom, your dad, your sister, maybe 1 or 2 friends, done. Once the number exceeds it, and the total, we humans, right, we have a capacity of around 150 people. At any point of time, maximum you can remember around 150. That could be anyone, right? Or that the person who is taking you every day to your class, that car driver, or maybe the newspaper guy. In total, there are 150 people maximum. Like that is your RAM capacity. As the number becomes too big, right? You don't even know. Someone will come and say, "Do you remember I'm your school friend? Ha, I saw you somewhere." That's what happens. It happens with me a lot. So every year, if you see, I have so many students every year. So once your batch passes out and the new batch comes out, my memory starts fading. So, your seniors come and tell me who are 7, 8 years back, sir, do you remember me? I was like, first of all, your faces will change a lot. That is a big problem. People become tall, people faces change a lot. I can't even recognize, first of all. So that is the thing actually. So there are 5 people whom you can have a very strong relation, and 150 is the max number, and after that you're gone. Your memory can't keep up. And then some people have Instagram with 3,000, 5,000 friends. So the electrostatic repulsion due to protons. So I think generally, right, this thing, the repulsion starts, dominating somewhere around from lead. Lead is the last stable nucleus that we have so far. After lead, every element is radioactive, meaning they're just waiting for a chance to break down and become lead due to protons becomes large. So this is the reason for the radioactive decay. This leads to decrease in stability. And emission of radioactive particles. The reason is that only. So the protons on the edge, right, have a very limited nuclear force. So this is the problem. As the size becomes bigger and bigger, your nuclear force cannot increase, but your repulsion force will keep increasing. Clear with this? So then what people observed, whenever you take a nucleus, for example, if you take something like, neon, it has like 10 protons and 10 neutrons. What people noticed, when they took 10 protons ka mass and 10 neutrons ka mass and added them, whatever mass they got, and when they took the mass of the neon ka nucleus, they observed the mass of the neon nucleus is slightly less than the individual masses. It's like 1 plus 1 is slightly less than 2. Something of that sort. So the masses are not adding up. People found out there is a mass defect. And they noticed this with everything. Matlab, every nucleus had this problem. And the first thing they didn't understand was like, why is the mass decreasing? And actually, if it is decreasing, where is this going exactly? That is where we come up with something called binding energy. So whenever you combine the small nucleons, smaller elements into bigger elements, you lose some mass, and that mass becomes energy. And more mass you lose, more energy you lose. And remember, we studied the statement: every system in the universe will try to achieve a state of least energy. So by losing more energy, that is by more mass, you actually become more stable. Mass defect, which is nothing but the theoretical mass. This is the main concept, right? Which is easy, like 3 statements, but I'll show you how the questions will be asked. The theoretical mass minus experimental mass. So the theoretical mass will be Z into mass of the protons. Z is the number of protons. Plus A minus Z is the number of neutrons. So we write delta M, which is your mass defect. Z into mass of the protons plus A minus Z into mass of the neutrons minus M experimental. This will be given the experimental mass. There, this is your first formula to remember. Second one, actually, after the radius of the nucleus, this is your second formula. And people, right, they figured out in the experiments, whatever this mass that was going off, this is actually becoming energy. So after the reaction, where do you get that energy? Now we know in sun, hydrogen combines to form helium. So where are you getting all that heat that is being generated from the sun then? So that is actually coming when the hydrogens become helium, they lose a small mass, that mass is becoming energy. And that's what is being emitted as photons from the sun. That means every second sun is losing mass. Yeah, so we define this thing as binding energy. Which is delta M into C square. But generally you get this thing in AMU. So we can write delta M into 931.5 million electron volts. If you take delta M in AMU, you can get in electron volts. If you take it in kgs, you have to multiply with C square. So binding energy ka definition is an amount of energy required to separate the nucleons. That means if you take helium, if you want to separate the 2 protons and 2 neutrons completely, you need to give this much energy. This is your second formula, binding energy. And the stability depends on, so how stable the nucleus will depend on. Think about this. If you have a high binding energy, this is a binding energy per nucleon is proportional to stability. How much energy is required to remove one nucleon? So when I say nucleon, it can be a proton or a neutron. So binding energy by atomic mass. Think of like this. Let's say we have two group of people. Okay, there's a group of 3 who has 10,000 rupees. There's a group of 10 people who have 20,000 rupees. In which group you want to be? The group of 3, right? Even though the money is more for here 20,000, but per person the group of 3 has more money, isn't it? So binding energy per nucleon is a better factor for stability than binding energy. How difficult it is to remove one nucleon, because after removing one nucleon your element will change. Either it will become an isotope or something else. There, all three formulas are related. Once you get the mass defect into 931.5 is binding energy. Binding energy by A will give you the binding energy per nucleon. These are the three main formulas. The theory is pretty easy, but let me show an example how this works. Any doubt so far? Let me show you a question. The problem with these questions, right, are the numbers. So there, this is how they'll ask you. Find the binding energy of ferrous ka iron gun nucleus. Atomic mass of iron is 55.9349. You can see the decimals. Hydrogen is 1.00783. Neutron is 1.00876. They do ask. They did ask. I think in 2016, 17. I don't remember. In advancement, this was a paragraph question. Straightforward. Huh? Matlab, if you know how to multiply and divide, you get the marks. Most people got irritated with the calculations. So how to solve this? First thing, find the mass defect, delta M, which is Z into mass of the proton plus A minus Z into mass of neutrons minus M experimental. So for the iron, there are 26 protons, so 26 into 1.00783. You can't do approximations here because the difference will come so small. If you write this thing as 1 and this thing as 1 and this thing as 56, you'll get 0. You'll get nothing there. And this will be 30 protons here. 30 into 1.00876 minus the experimental mass is 55.9349. Once you solve this, you'll get a number. So the working would look something like this. You can see the numbers there. 55.9349. If you subtract this, you'll end up with this number here. 0.5287 AMU. That's your mass defect. Once you got the mass defect, the binding energy will be delta M into 931.5 MeV. That's 0.5287 into 931.5. That is 492.55 MeV. It's concept is pretty straightforward. The numbers are the bad. Subtraction, multiplication, and this thing. Clear with this. This is the total binding energy of the iron nucleus, meaning if you give this much energy, you can separate all the neutrons and protons from that ion and make it into individual protons and neutrons. Clear with this. That is the headache of this part of the chapter, calculations. And if they ask, there is no way out, you have to solve. Clear with this? And I don't think means they'll allow you the calculator also. There's no calculator allowed. So let's see one more example. Hmm. Just write the equations and leave it. Take a minute. Just write the equations. The numbers are anyway bad. Now they're asking binding energy per nucleon. So when they ask you binding energy for a nucleus, they are talking about the calcium and between that individual protons and neutrons. Wrote it down. The working will look like this. And this is that same thing. There. So mass defect will be this. Substitute the numbers. You will get mass defect is 0.3672116 decimals. Multiply with it 931 and divide by 40. You'll end up with this. Straightforward. Matlab, like I said, you won't have issue with the concept. The numbers are the issue. And imagine there is a full advanced paragraph based on this. Clear? Then, so that is about mass defect binding energy for for a nucleus. If you actually look at the stability, you will notice something. There. So this graph is important. This is the graph of binding energy per nucleon versus atomic number. So if you look at hydrogen, can you see how low it is? That is for deuterium. Because in a deuterium, only hydrogen doesn't make sense because in hydrogen there is no nuclear force. Deuterium will have one proton, one neutron, so you will get some binding energy. So it starts with deuteron 2H1, and look at helium. Suddenly helium becomes pretty, the stability just bumps up. If you see the numbers around 1 to almost 7.8 ke aspas, matlab it becomes 8 times more stable. And then lithium will decrease, carbon will increase, nitrogen will decrease. You can see the zigzag thing. This thing has more to do with the packing. Even number of particles can be packed in a more systematic way, so you get more nuclear force. Odd number of particles, the packing will be a problem. And you can clearly notice here, iron will be the most stable nucleus. So just read the whole thing, then I'll tell you what are the important points on this page. Just go through the whole thing for a minute. Done. So few points. First thing you'll observe, the minimum value of binding energy is for deuteron. Theoretical questions. The maximum value is for iron. Be careful, iron is not the most stable element. If you take iron and keep it outside, it gets oxidized. Iron has the most stable nucleus. Don't get confused between a stable element and a stable nucleus. Right? And if you see around, this is the stability region. Around this range, everyone wants to be in that range. That is a most stable thing. And you can clearly see this is again a minimas are associated with the nuclei with the odd number, and again theoretical one. Maximas generally have a more this thing. So when the nucleus number exceeds 220, they start becoming unstable, because of which the heavy nucleus breaks into identical particles. Right? This process is called nuclear fission. This is what we see in the nuclear reactions currently. So you take a heavy nucleus of uranium and you break it into smaller pieces. Similarly, the niter nucleus will combine, right? And this process is called nuclear fusion. So basically, it is pretty simple. If iron is the most stable nucleus, everyone who is smaller than iron, what will they try to do? They'll try to combine to become iron. Everyone who's bigger than iron, what they will try to do? They will try to break down and become iron. Given a chance, they will do that. But the reason why they don't break down immediately is because, in chemistry, activation energy. See, if you take a paper, right? If you burn down the paper, it will become ash and carbon dioxide. That means the ash and carbon dioxide is more stable than a paper, right? Then why don't all the paper in the world just suddenly burst into flames? Because you need to provide an activation energy. Even though the products have less energy or more stable, the reaction won't proceed because you need to give a certain amount of energy. I hope you remember that activation energy. So that is a reason these things will just don't break down. If you have something like gold, gold will not break down and become iron automatically. That would be horrible, right? People will start going mad. You buy gold chain, next day it becomes iron chain. Anyway, so few points. You just need to remember this for theoretical questions. This is the same point which I said. So lighter nucleus will try to combine. We call this thing nuclear fusion. So currently, we humans have achieved nuclear fusion. One, when you talk about thermonuclear bombs, what they do in the thermonuclear bomb, first we blast a fission bomb. That increases temperatures to around a million Kelvin. In that process, you get a fusion reaction that will release even more energy. These are your thermonuclear bombs. Hydrogen bomb, if you heard about the term. Atomic bombs, hydrogen bomb. Hydrogen bomb is a fission plus fusion. So what these people used in Japan are atomic bombs. It is only fission based. It's actually like a small bomb. It just wiped out a city, but it is small. The current bombs that we have, right, these hydrogen bombs, they're 2 lakh times more powerful than Hiroshima and Nagasaki bombs. 2 lakh times. That means it is like a small, that firecracker, Diwali cracker jaisa lagega abhi, compared to these things. So the bombs we have right now, they can wipe out states. Meaning entire Maharashtra goes off, entire southern coast goes off. Hiroshima and Nagasaki were like small compared to what we have. That is one. Second thing, Korea, they actually succeeded in creating a nuclear fusion reactor. Right? It's a tokamak design. We'll talk about that a bit later on. So, but the problem is, there's an experimental, meaning for every 1 unit of power, you have to give some power. You are getting 1 unit of power. It's a 1:1 ratio. For to make a commercial nuclear reactor, right? We need, if I give 1 input, I need to get 300 output. That would be profitable. So far, we have not done that. They're building one in France now, ITER. This is the world's first biggest nuclear fusion reactor they're building from almost 20 years. They'll complete it by 2035. So that would be the future. If you don't build nuclear fusion reactors, humans will go extinct in the next 100 years for sure. Where are you getting so much power from? We don't have any proper power sources. If you actually think about humans, right? Think about human civilization, how we did advance, okay? Initially, when we are cavemen and cave people, right? What did we do? We relied on human power. We are taking, the sticks and everything, and we are hunting animals. And we did that for almost thousands of years. The first time we started building something properly is once we started domesticating animals. We domesticated cows, we domesticated horses, we domesticated animals, right? And then agriculture started. For plowing, we needed carts, right? Cows or hogs or whatever. For transport, we needed animals. You couldn't carry so much luggage on you. So we started building small societies like a village, a small city. During that time, a city means a people of 3,000, 4,000 people is like a huge city. And this went on for another thousands of years. And if you see, right, a person who's living in 1000 AD, a person who's living in 1500 AD, there's not really much difference in life and quality of life. Almost for 500 years, everyone lived the same. Matlab, there was no difference only. But think about this 20 years back and 20 years now, isn't the life difference in life is so huge, isn't it? I saw that when I lived, right? If you see, I belong to a generation where I've seen the transition. Right. When I was in school, phone was a luxury. If you had one phone, matlab, in your society, if you have a phone, you must be a very rich guy. Right? Getting a phone connection, you need to get, MLA ka recommendation. It was a big deal. And then phones became common, landlines. And then after landlines, having a mobile is like a super big deal. Then now to nothing. Every kid has a phone now. Right? And then think about this. We humans, right? We started developing rapidly, when industrial civilization, we started with the steam engine. That was the first thing. As we got access to more power, right, humans started developing rapidly. When we didn't have any power, right, we depended on human ka power. We were just hunting animals. Once we got access to animals ka power, you started using horses and dogs. We started agriculture. We started building houses and small societies. Once we started getting access to steam engines, we started building railways. We started connecting cities. We started transporting. We had steamships. The civilization started expanding rapidly. Steam went on for another 100 years. Then we got petrol engines and diesel and everything. But steam was still the main thing. Even today, if you see, steam is still the biggest factor. All thermo power plants that we use, they burn coal to get steam, and from there we get electricity. And the next step was nuclear fission power. 1940s and 50s, that's when we started developing nuclear reactors. That was the next access. So that was the next level of energy. It's like playing a game only. You're getting access to higher and higher levels of energy. So every time the civilization wanted to improve, the first thing you need to see is how much access does the civilization have access to energy. Just think about this. If you just look at in your house only, how many devices each person has? Everyone has a mobile. We have 2, 3 laptops in the house. There is a TV, there's a micro oven, there is a refrigerator. So if you just look at the power consumption in your house, think what would have happened. It's a huge power consumption. And this will not stop. This will just keep going on and on and on. You know what is the biggest problem for a development of AI? People keep saying AI, AI, AI. But you know what is the actual biggest roadblock? Electricity. To run that AI ka chips, you need a huge amount of power and cooling systems. Where do you get all this electricity from? And the current estimate, right? The amount of power this AI is going to use will be more than, right, whatever we are consuming right now. They will just exceed the quantities. Why all that? In ChatGPT, right? Every time you do a search, the amount of energy it consumes for that one search is almost, it consumes a lot. Matlab, you can actually boil around 5 kgs of water or something. Every time you do a search, you are actually wasting so much energy. So the story goes on like that. That is the biggest cost for this AI or crypto mining or whatever these things you see. It is all about electricity. So at the current rate we are going, right? So far we are able to provide electricity, but I think another 40, 50 years, if we don't create any new energy sources, we will be stuck. We will again, the advancement of civilization will again stop. Nuclear fusion reactors is the key. So that is the meaning of that. If you don't have fusion reactors, we are going to go extinct in another 100 years. That's for sure. But anyway, we are so busy fighting for all other random stuff. Who cares about fusion reactors? Right? Salman Khan, what he did in the movie, that is more important than bloody fusion reactor. So then we have nuclear collisions. So if you actually create fusion reactors, whichever country has fusion reactors first, right, they'll be the next superpower. Solar power, people keep talking about solar power, but in order to create the solar panels, how much pollution we create. The solar panel, right? The amount of energy you use to make a solar panel, it creates, by the time the solar panel life gets over, it only produces around 0.9 times to 8 times of its energy to be created. So actually making solar panels takes more energy than what you get from solar panels. And the only reason solar industry is working is because government gives subsidy. Government, right, gives subsidy because they made a rule like, we are going to become a renewable source of energy karke bullshit and everything. So if you actually open a solar company, 100 rupees ka solar panel, government will give you around 50 rupees. You're actually investing only 50 rupees. Because of this, it is profitable. And all solar panels are imported from China. And all these things are made from rare earth metals. And rare earth metals will create immense amount of pollution. All these EV vehicles, all this battery, everything requires hell lot of pollution. For every 1 unit of pollution they decrease, they create 5 units of pollution. And no one wants to talk about that because it's not profitable, right? And who gets the solar contracts? A minister ka, son-in-law, minister ka something and everything. They get the contracts. You bid a contract for 200 crores. The government will give you 100 crores. In that 100 crores, you give 25 crores as bribes. 25 crores, you build a small solar thing. 50 crores, you keep it in your pocket. When they come for inspection, you say there is a big storm and all the solar panels got broken, so there is nothing left. Done. Case closed. You made 50 crores profit without investing a single rupee. That is how solar farms run. Half of them, more of them. What? You really think people are interested about generating solar power and save the humanity and all bullshit? They're not like old school, huh? People don't take bribes directly nowadays. Let's say if you are Mumbai ka mayor and you want to take a bribe, or you want to make money, what do you think you should do? So you take one of your relative, right? Give them a contract for a nice road in your locality. He will build a road which will get spoiled every 3 months. Every 3 months, immediately he'll come and repair. So every time he closes the pothole, the charge is only 4 lakhs. You know that? So one night before someone will come, dig a hole and go. Next day you come and fill the hole, you get 4 lakhs. The cost of building the road, 10 crores. After 1 year, maintenance of the road, 30 crores. No one build a proper road because if you build a proper road, it will stay there for 10 years. How are you going to make money? So that is how you take profits. That is how you take bribes indirectly. No one actually exchanges cash. Everything is legal. I built a road, there's a pothole, I repaired it, it costed 4 lakhs. Seriously, to close a pothole, you cost 4 lakhs per pothole. Anyways, so A plus X, this becomes Y plus P. So if A is your bombarding particle, you will realize all these things once you're done. Things work differently outside. So X is your parent nucleus. This Y is a daughter nucleus. So whenever this bombarding particle goes and hits this nucleus, it transforms into a different nucleus and it emits a particle. So if you take this mass to be m1, which is velocity v1, remember one thing: in nuclear reactions, right? Momentum is always conserved. So this is before collision, and this is after collision. So in nuclear collisions, you can conserve linear momentum. Energy plus mass is conserved, and conservation of charge. So let's see how this works. So first thing, by mass energy conservation. So how do you convert mass and energy conservation? You basically convert everything into energy. See how we write this. So the kinetic energy of the particle is K1. So initially, let's say A is moving, B is also moving. This is the kinetic energy of reactants. Plus mass of the bombarding particle into C square. So you convert all the masses into pure energy. Mx C square. This should be equal to the kinetic energy of the products, which is K3 plus K4. Plus mass of the Y, the daughter nucleus into C square, mass of B into C square. If you rearrange the terms, you will notice this is K4 plus K3 K1 plus K2 will be equal to MA plus MX, MY plus MB plus C square. You can clearly see this is nothing but change in kinetic energy. And this is nothing but mass of reactants minus mass of product is the mass defect. That means whenever this bombarding particle goes and hits, some mass again will be lost and that mass becomes energy. This thing is called as Q value of the reaction. It's like in a chemical reaction, we say, right, heat released in a reaction or heat absorbed in a reaction. But this is at a nuclear level. So Q value of a reaction is given by mass defect into C square. I'll write down a more usable formula in the next page. And how do you get this energy? Think about this. Whenever you burn something, we say heat is produced or something. But for a nucleus, there is nothing called heat and all. So whatever energy is released in the form of kinetic energy. So whenever that mass disappears and you get energy, that becomes actually energy of the kinetic energy of the particles. In the form of kinetic energy of products. We'll write down that. Take a small break, come back with 7:10. Continue from here. Any doubt so far? So I'll come back in 5 minutes. Chalo, let's start off. So if I write this Q value, this is another important one. Mass defect into C square. So this is mass of the reactants minus mass of the products into C square. Basically, this was the same thing as binding energy for a nucleus. You getting it? So if you take for a nucleus, right, example, the protons and the neutrons will be the reactants and the nucleus will be the product. So the example, if you take calcium 40 Ca20, you can write like this. Let's say we have 20 protons plus 20 neutrons will become 40 calcium 20. So here the Q value is nothing but the binding energy. So technically both are same. Q value is the binding energy of calcium. Sometimes people get confused. The binding energy, Q value, what is it? So generally we say Q value when you are combining elements, like let's say example, sodium plus something becomes something else. But if you do that fundamentally for this protons and neutrons on this thing, the same thing, the binding energy is called as Q value. So just be careful, don't get confused. It is nothing new. So we call it binding energy when you talk about a single nucleus, but when you combine elements, we call it a Q value. So technically it is still the same. Another way of writing this thing is using binding energy. Sigma of binding energy of product, sigma of binding energy of reactants. Now be careful, if you use mass, reactants will be has more mass than products. But if you use binding energy, products minus reactants. Because what is binding energy exactly? Binding energy is actually negative of the energy. So because of the minus sign, it becomes like that. What is the meaning of that? Binding energy is negative of the energy. Example, what is the energy of an electron in the hydrogen atom? It's minus 13.6 eV. Energy is actually negative. The meaning of negative energy is if you supply 13.6, you can remove the electron. Same question if I ask you like this, what is the binding energy of electron in the hydrogen atom? We'll say plus 13.6. So the moment you use the word binding energy, the minus sign is taken care of. Hope you're getting the difference. So this is a very important formula. If they give you the question, if binding energies are given, products minus reactants. If masses are given, reactants minus products. So be careful with that. And that minus sign difference will come because the binding energy with the negative sign is taken care of. If Q value is positive, In chemistry, you call it exothermal reaction. So here it is, energy is released. There is a name for this. It's called exoergic reaction. And if Q value is positive, energy is absorbed. This is endoergic reaction or endothermal reaction. That is fine. It's just a terminology. So you have to provide energy for the reaction to happen. Let's see a few questions on this. There, this is your, so how many formulas still I had to remember? First thing was the radius of the nucleus. Second thing was the mass defect, binding energy per nucleon, and the Q value. So like 4 things. This is a good one. Let's try this. This is a doable one. No big calculations, nothing. Think. Let's see what you'll think about this. I'll give you a minute, then I'll show you. Let's see. Now let's try to read this thing. So we have radium, which will become radon. So radium, which is 226. Let's initial it is at rest. This thing breaks down into an alpha particle, which is helium, and radon, which is 222. So both of them will fly away in the opposite directions to conserve momentum. P1 is equal to P2. Conservation of linear momentum. And we know kinetic energy is nothing but P square by 2m. So kinetic energy is proportional to 1 by mass. So kinetic energy of radon by kinetic energy of alpha particle is nothing but the ratio of 4 by 222. So kinetic energy of the radon will be 4 by 222 into kinetic energy of alpha particle. Now, what is Q value? If you remember, Q value fundamentally is nothing but kinetic energy of the products minus kinetic energy of the reactants. Like I said, whatever energy that you're releasing, it is actually released in the form of kinetic energy. There's nothing called heat and all that stuff. Heat is nothing but molecular kinetic energy. And reactance is 0 because it is not moving. So kinetic energy of the products is nothing but kinetic energy of alpha particle plus kinetic energy of radon. Therefore, the Q value will be kinetic energy of alpha is 1 plus 4 by 22. Kinetic energy of alpha is given 4.78 into 226 by 222. And this comes to around 4.87 MeV. Options will be pretty close by, so you have to be careful. You'll get around 4.866, we round it off to 4.87. If you see, this is more of a momentum problem than Q value and all that stuff. Clear this. Not a tough question, but you should know what you're doing. That's what I keep saying. You need to solve at least 10, 15 questions on each part of the thing. Then you'll get the hang of it. Questions are not tough. You will not even understand what the hell is happening in the exam. You will see the Q value and you'll start assuming something else, but end of the day, this is a momentum problem. All clear with this? Let's see one more. This was an old PYQ. Where is this? This one, it's a good one. There have been, questions of this sort based on this model. Look at this. They gave you a graph of binding energy per nucleon versus the mass number. They're asking in which of the following 4 reactions energy is released. Again, remember what is Q value? Binding energy of products minus binding energy of reactants. So if your products have more binding energy than reactants, you get energy released. Simply think of this. What is binding energy? Higher the binding energy, more stable you are. So think about this. If you become from unstable to stable, then your binding energy should increase, isn't it? Because it's more negative energy, if you think about it. Your energy is becoming more negative, means you're losing energy, you're emitting energy. How will you do this? Think for a minute. I'll tell you the easy way to do this, but we will also calculate and show it to you so that you get a hang of it. You need to know how to calculate binding energy for each process. Now see, one way to guess this, we can clearly see Y is the most stable nucleus, isn't it? Means everyone will want to become Y. Making sense? Now look at the options. Y is becoming 2Z. That doesn't make sense, isn't it? Why will a stable nucleus decay and become less stable? The first option is wrong. Second option, W is becoming X plus Z. I'm not sure. Maybe. C is a very clear answer. W is becoming 2Y. The unstable is becoming 2Y stable. Making sense? So luckily in the exam, if it's a single choice question, you can just mark C and go ahead. Because definitely C will release energy. Remaining, I'm not sure. Okay, but let's calculate and see. I'll show you one, then you calculate for the rest. So Y is becoming 2Z. What is Q value? Binding energy of products minus binding energy of reactants. Here, what is the product? Z. Look at Z here. Z का atomic number is 30. 5 is the binding energy per nucleon. मतलब each nucleon has an energy of 30 and there are 5 and there are 30 of them. So product, it is 2 into Z. So 2 into 5 MeV per nucleon and there are 30 nucleons. Are you getting how to write that? The total binding energy of Z is 30 into 5. So that is binding energy per nucleon into nucleon will give you the binding energy. And what about the reactants? Y, that is 60, 8.5 into 60. This would be 300. This would be 510. So this would be minus 210. Yeah, negative number. So this is wrong. This is an endothermal reaction. Are you clear how we calculated this? Can you do the same for the remaining three? Let's calculate and see. I want you to get used to this calculation because later on you will see in advancement, you will get some, hypothetical graphs. They will say the energy is becoming like this, then find the energy released. So you need to understand what you're doing. Calculate, I'll give you a minute or two. B, C, D. But I already told you how to get the answer easily in the exam. B is minus 30. That looks right. Okay. W is becoming X plus Z. This would be X ka binding energy is how much? 90. 8.5 plus Z is 35 minus W, which is 120 into 7.5. This is minus 30. Check. So that is also gone. W is becoming 2y. Two into y will be 60 into 8.5 minus W will be 120 into 7.5. This is around 120. D will be, you can calculate D also. Then that is how you get the answer. Clear with this. Yeah, last one is minus 60, it seems. This is one important model. They'll give you a graph. So This is one model. It's just based on momentum. This is a second model. They'll give you a graph and they'll ask you Q value. The third one, this is another important one. So I'm showing you all the non-standard ones. Standard one, same thing. Apply the formula, you'll get the answer. Let's get this thing. A is a standard one. B, something happens. First, you try. Just write the equations. Don't worry about the numbers. Let's see. The thing here is, first thing you need to understand something. What is atomic mass? Just give me a minute. One. So listen. So atomic mass is what? This is the mass of the nucleus plus mass of the electrons. When you say mass defect, what are you subtracting exactly? Mass defect is change in mass of the nucleus. Generally, this does not create any issue. Generally. But something happens here. Now see how to write this exactly. For the first one, when I write, so what is the mass defect here? Delta M will be sigma mass of the reactants. So remember, when you subtract masses, we subtract reactants minus products. When you take binding energy, products minus reactants. Again, when mass of reactants of what? Of nucleus. That means for the first reaction, you can see oxygen becomes fluorine plus an electron. This is mass of oxygen nucleus minus mass of fluorine nucleus. But if you see the values there, these are atomic masses. Matlab, these masses also include electron ka mass plus mass of an electron. So how to get the mass of a nucleus? Mass of oxygen atom minus, and oxygen has 8 electrons, 8 Me. This is mass of fluorine minus 9 Me. So from the atom, if you subtract the electrons ka mass, you might think that it is too small. Will it affect? It does affect. Because these numbers, if you see now, you are calculating up to 5 decimals, the electron ka mass becomes actually sufficient. And luckily, if you observe here, electrons masses will cancel out. You end up with mass of oxygen atom minus mass of fluorine atom. That's your mass defect. Now, if you do the same thing for the B part, you will see something else. So delta M, so this will be mass of aluminum at nucleus, so aluminum atom minus aluminum has 13 electrons, mass of magnesium atom, it has 12 electrons plus 1 positron. If you do this, you'll get mass of aluminum atom minus mass of magnesium atom, and you also get minus 2 Me. You always get that extra 2 Me whenever there's a positron emission. So it's very important. That is a question they can ask you even at an advanced level. They'll put a positron. Most people just subtract the masses. They will mess up this part. So just be careful with that. In positron emission, you will have that issue of 2 Me. Because most of the time they'll give you the mass of the atoms only, atomic masses. But we don't need atomic masses. We need nucleus mass. Clear with this? So the working will be like this. This is the whole working with numbers. So even if you see some textbooks, now they'll directly write these equations, and you will be like thinking like, how the hell did you get this extra 2 Me in this equation? That will be the issue there. Check it out. It's the same thing, but the numbers are bad. So this is one thing you have to keep in mind. Whenever there's a positron emission, there is an issue. Clear? Let's see one more like this. This time you guys just write the equation. Just write the equation. We'll not simplify this. Lithium plus proton gives you 2 alpha particles. Just find the mass defect. If you got the mass defect, you can multiply 931.5, you'll get the energy released. All that part is fine. The headache is always the calculation only. So if you see here, the mass defect, that is lithium ka nucleus you need. So mass of lithium nucleus plus mass of proton minus 2 times mass of alpha particle. But here he didn't give you alpha particle, he gave you atomic masses of lithium and helium atom atomic mass. So this will be M lithium atom minus 3 Me plus Mp minus 2 mass of helium atom. Each helium has 2 electrons, so 2 Me. Lithium atom plus Mp minus 2 mass of helium atoms plus 1 electron. Clear that? Right, Advait. So just be careful with that thing. When you do mass defect, you're always interested in the nucleus mass, not the atomic mass. This is one type of model they can ask you. So there are 3 different models in the Q value. They'll give you something of this. So there are no calculations. It's based on momentum, graphs, and this positron emission. The 4th type of question is this thing, endoergic reactions. endoergic or endothermal reactions. So these reactions, we have to provide energy. Bombarding particle must have enough kinetic energy for a reaction to proceed. That means, let's say in a particular reaction, you have to supply energy. Let's say you have to supply 100 MeV. So how much energy should this bombarding particle have so that the reaction will occur? So let's say we have a bombarding particle, let's say X, and let's say this becomes Y. I'll take an example problem also. Let's say this is at rest. This is your target. This is your bombarding particle. And here the Q value is negative. The most general mistake is this. If the reaction has to proceed with 100 MeV, then people think that bombarding particle should also have 100 MeV. The problem with that statement is, let me ask you this one question. Let's say we have an ice block, which is fixed. Second case, we have a same ice block, but this time it is on a smooth ground, free to move. In both the cases, a bullet of mass m goes with speed u and gets stuck in the ice. You heard in the scenario, two ice blocks, one is fixed and one is free to move. In both the cases, a bullet of mass small m and speed u goes and hits the ice block and gets stuck. All the energy lost becomes heat, in which case more ice will melt. Is the question clear? So we have two ice blocks, one is fixed and one is free to move. A bullet of mass m, everything else is same. The only difference is fixed and smooth. The bullet will go into the ice block, get stuck, and whatever energy is lost becomes heat, and that heat is used to melt the ice. In which case will you melt more ice? Or is it same? Cams on, everyone. Others, keep your cams on. Now let's see what happens. Because this thing is fixed, half mu square becomes heat. Second case, because it is free to move, after hitting, both the ice and this thing will go with a common velocity, which is mu by m plus m. Did you observe something? Some part of the kinetic energy is still left over. So the heat will be how much now? The heat will be half m u square, the initial energy, minus half m plus m v common square. Can you clearly see in the second case you produce less heat than the first case? The problem is, if all the kinetic energy becomes heat, that means the center of mass velocity is zero. That means momentum is not conserved. Are you clear? Something similar happens here. So when you're going and colliding with the nucleus, your entire energy cannot become Q value because momentum will not be conserved then. So let's take it in terms of collision. So we have particle MA, which is going with some speed u. We have a target here, MX, which is at rest. This is the scenario before collision. After collision, this thing will come and stick here. They both go with a common velocity. This we already did previously. Do you guys remember? Atomic collisions. What is the maximum energy lost? I gave you a short formula. Half mu v relative square. Do you guys remember this? The energy lost is half mu v relative square. Mu is nothing but reduced mass, which is mass of the bombarding particle, mass of the nucleus by ma plus mx into u square. This much energy will become lost. And where will this energy go? This will actually become to the Q value. So this much energy will be absorbed for the reaction to proceed. So from here, we can write this thing as half ma u square mx plus ma is equal to Q value mod, because it's a negative thing. And this half ma square will become the kinetic energy of the bombarding particle. This becomes Q value 1 plus ma by mx. there. So if the Q value is 100 MeV, you can't give 100. You have to give more than 100 for the reaction to proceed. This itself is an advanced question. The theory which I explained here is an advanced question. Same thing, you can, after the collision is over, the kinetic energy of the products, you can calculate that. That will be half Ma mx Vc square. That would come out to be Q into Ma by mx. So it's fine if you don't remember this, but you should know how to derive this. Ma is the mass of the bombarding particle. Mx is the mass of the nucleus. Yeah, have a look at this page. This is nuclear collisions. In atomic collisions, whatever energy was lost, that was used to excite the electrons to higher orbits, and you got photons, remember? But when nucleuses collide, that energy is used to become mass. So all this energy actually becomes mass. So if the Q value is negative, the mass defect is not negative, mass defect is positive. The system ka mass increased. And how did the mass increase? The energy got converted into mass. So that is a difference. In nuclear collisions, mass of the nucleus changes. In atomic collisions, photons will get emitted. Everyone clear with this? This can be a pretty good advanced paragraph question. Let me show you how they will ask this. But everyone got this. Again, if you see, it's more of a mechanics problem, isn't it? Look at this question. This would be good. If it is a mains question, I'll ask you A and B. If it's an advanced question, I'll ask you C and D. And numbers are bad, so I have to take questions from everywhere. Look at those numbers, 5 decimals. Just write the main equations and leave it. Try. I'll give 3 minutes. At least first two parts, you should be able to write the equations at least. This is actually oxygen. First was easy. One P1 plus 15 nitrogen 7 AXZ is 1 neutron, 1 and 0. 1 plus 15 is A plus 1. A is 15, and you can clearly see Z is 8. This is a 1508. This is an isotope of oxygen. You got A ka value. What is B ka value? Q value will be the mass defect, delta mc square. So this would be how much? Mass of the proton. You can just subtract it. Mass of the proton plus mass of the nitrogen minus mass of the X element plus mass of the neutron, cos C square, 931.5. Now, since you know the C part already, you can directly do this. So kinetic energy of the bombarding particle will be the Q value, which will come out to be negative in this case. 1 plus mass of the bombarding particle. Here, that is a proton which you're bombarding, and mass of the nitrogen. There. Clear with this? That will be pretty straightforward. D is an interesting one. Now, D is what it makes it tough. If the proton has twice the energy, the minimum, And after collision, the neutron becomes at 90 degrees. Means this is not a head-on collision, it's an oblique collision. Then he's asking, find the kinetic energy of the nucleus. Can you think about that? I'll give you a minute or two. And this is not the first time. You have seen something like this before. Remember atomic collisions? It was something similar. The neutron hits the helium and the neutron goes at 90 degrees. Similar. Just think about a minute or two, like how will you approach this? And I'll show you. We have to draw a picture always. So the moment you hear about these collisions and all this stuff, angles 90 degrees, momentum conservation. This is the whole working. So Q value will be this, which comes out to be minus 418. That is your endothermic reaction. And the formula here. And there, this is the thing. So it's going like this. This is the proton. This is at rest. After collision, one thing goes up and one thing, this is your neutron, which flies away at 90 degrees. And this is that oxygen 1508. So we can conserve momentum in the x direction. We can conserve momentum in the y direction. We got cos theta, sin theta, square them on both the sides. Cos square theta plus sin square theta becomes 1. You end up with this equation. Energy conservation is second equation. Solve them, you'll get the answers. This is the trick. Always remember, whenever you have oblique collisions, that they'll always give you 90 degrees generally to keep your life easy. You'll get cos theta, sin theta. You can simplify and get the answer. Because if they don't give 90 degrees, if they give some other angle, then you can't write this cos square theta, sin square theta won't come off that easily. But this is a general thing. They can give solvable, little lengthy. Exact same thing we did here also. Remember, conservation of momentum, horizontal direction, vertical direction. I squared them and I got this. Same concept we use there. Check it out. This is the fourth model in this Q value. These four are important models. The positron thing, endoergic reaction, the graph, and that momentum conservation and all that Q value based. If they want to twist something, they'll play around something of this sort. Clear with this. This would be a good advanced paragraph. And the last thing is a nuclear reactor. So again, a lot of theory. You should have an idea about the nuclear reactor schematic. You get a lot of theoretical questions on this. So this is a nuclear reactor schematic. So I'll just color a few of them. So this red thing which I'm coloring is the control rods. So these control rods are cadmium boron rods. They do ask. There was a question like this in CET means or somewhere, some exam, like what is the control rods made of? People have no clue what is control rods. We'll talk about that each one. These are uranium rods. So these are filled with this uranium pellets. Now the thing with this uranium thing, right? It will give a lot of energy and everything, great, but we have a big problem actually. Whenever you mine for uranium, you actually get two isotopes, 238 U92 and 235 U92. And whenever you dig this, we have observed this everywhere. We always get 99.3% of U238 and 0.7% of 235. Means if you dig 1 million kgs of uranium ore, 1 million kgs, you might get around 100 grams of uranium. First of all, it will be that inefficient. Like you have to dig like anything in order to get 100 grams of uranium. In that 100 grams, 0.7 grams is 235, 99.3 is 238. Unfortunately, our headache, only 235 undergoes nuclear fission. 238 does nothing. It's just stable. It just doesn't break or nothing happens for that. This undergoes nuclear fission. 238 does not undergo nuclear fission. So that is one big problem. The problem is, how do you separate 238 and 235? Because chemically they're exactly same. There is no difference between 235 and 238. You cannot separate them chemically. There is no way. Whatever 238 does, 235 does the same thing. So people have come up with, there is only one way to separate this: diffusion. Because 235 has slightly less mass, the molecule will go slightly faster than 238. So what they do, you cannot take directly uranium. So you first react it with fluorine. You create a UF6. So uranium actually forms 6 bonds with fluorine, creates a UF6 molecule, which is actually a highly viscous corrosive gas. They take this gas and they send it through pipes. Concept is simple. It's like a race between 238 and 235. Because 235 is slightly, faster, it will reach at the end faster than 238. But the difference is so small, right? If you make it travel 1 kilometer, nothing happens. They will make this gas travel 50, 60, 70,000 kilometers. They'll take the gas, send it through the pipes. They'll take the gas, send it through the pipes. They just keep doing this non-stop. That's why extracting uranium is one problem. After that, separating them is another big headache. They have to send this through, kilometers, like thousands. We are talking about 100,000 kilometers. They use centrifuges. They use different techniques. One of the reasons why terrorists don't have nuclear bombs, because the extraction of 235 is so difficult. If a terrorist, right, if the terrorists try to create a power plant, a nuclear plant to process them, it will release so much heat. It will release so much, energy in that area. You can easily detect a nuclear processing plant through a satellite. It's very difficult to hide such a power plant. Getting it? So, and the technology is very difficult. There are only very few countries in the world who can extract this thing. Now, after making it travel for a lakhs of kilometers, right, then you get 235 becomes 5%. Means it will be 5% 235, 95% 238. You won't get 100%, never. It's very difficult. 5% 235 is good enough for producing electricity. This is a, electricity grade uranium. If you want to make nuclear bombs, you have to make it 10%. That becomes even more difficult. And that's why processing this fuel is very, very difficult. We have the processing plant in Hyderabad. So if you see, our facilities are different places. So there, once we get that uranium, then we fill it in pellets. And this thing produces so much energy, you need not refuel this thing for 2 years. The power plant will work for 2 years non-stop, producing 24/7 power without a refueling. It produces so much energy. And that is the reason nowadays what we are doing, right? When we build these aircraft carriers, I hope you guys know that. Aircraft carriers, INS Vikrant and all the stuff which you're building. It's like a floating city. You have fighter planes on top of the ship and they're just flying off. The one we have right now, right, the regular one, whenever you start the engine, it consumes 10,000 liters of diesel. Can you look at that amount of fuel it consumes? 10,000 liters of diesel to start the engine. That ship has to be refueled every 3 days or 4 days. So there is like the aircraft carrier is going in the Arabian Sea. There is small, convoys which are coming, refueling and going. The ship has to be continuously refueled. So we have a problem. We have a range car problem. So now what we are doing, we are building nuclear aircraft carriers. So we have a nuclear power plant inside the aircraft carrier. The ship can travel for 20 years without stopping. No need to refuel for 20 years. All US aircraft carriers are nuclear aircraft carriers. So that is the reason, if you see this US aircraft carriers, they're just roaming around the world everywhere. India, we have a problem. We can't get out of Arabian Sea and Bay of Bengal. We have to be within that region for refueling. So same thing with submarines also. Submarines, when you build a normal submarine, every 2 days it has to come out to take air. But if you make a nuclear submarine, you have a nuclear power plant inside. You can take seawater and do electrolysis. And what do you get? Hydrogen and oxygen. You can use oxygen for breathing. You can use hydrogen for fuel cells to generate electricity. And you can make fresh water. The sailors inside can live for ever, basically, if the food is not a problem. And they have enough food for almost 4 months. So imagine a nuclear submarine just sitting under Karachi harbor, doing nothing and sitting for 4 months for an order. That is how you can spy on someone. So again, no need to refuel for 20 years. Only food is a problem for them. So that is a new tech. So old tech actually, but Indians now we are building it. Expensive and no one transfers the technology that easily. So again, a lot of theory there. So just listen. So nuclear fission. You guys can go through all this theory later on. See the main points. So basically 235 splits into approximately equal parts. So this is the reaction, everyone. No need to remember, but if you can remember, it will be great. Roughly have an idea. 235 U92, it absorbs a neutron 1 and 0, and it becomes barium 140 156. There are another ways of breaking, but this is the most common 192 krypton. And in this process, it releases 3 neutrons plus energy. And so if you look at the reaction, right, something interesting happens here. That means we have the uranium nucleus. The neutron, you have to send a neutron first. This thing comes and hit this uranium. In this process, this uranium will generate 3 neutrons. These 3 neutrons will go and hit another 3 uraniums. And then they will generate again 3 neutrons. And if you don't control this, this will become a chained, uncontrolled chain reaction. And this will just blow off. You get a huge amount of energy in a very short time. This is what happens in a nuclear bomb. You don't have control over that fission. It just keeps on. 9 becomes 27, 27 becomes 81, 243, and 3 power something. Within 10 fissions, you have 3 power 10 ka order of energy release. So this is what we call as a chain reaction. And if you don't control this, we have a is an uncontrolled chain reaction. So what we do here, we use control rods. So these control rods absorb that excess neutrons. So instead of getting 3 neutrons, you absorb 2 of them. So you maintain the reactions. To maintain constant power output. This is what we do in the power generation. So this is what happens with the control rods. So if you want to stop the reaction, you have to push the control rods completely inside. You want to start the reaction, remove them. This is what happened in the Chernobyl incident. The control rods, right? Something happened, the reactor started overheating, and the control rods, when they pushed inside, they started melting. And when the control rods are gone, there's nothing to stop the reaction. It became uncontrolled, and the overall thing went off. So that reaction is important there. So if you want to stop the reaction, this production factor K is less than 1. Matlab, you absorb all the neutrons. K is equal to 1, you maintain it. You want it to explode, K greater than 1. That's what happens in a bomb. Nothing there. It's all that just explanations there. Like I said, the main thing is the terminologies. You should know what is a moderator, what is a control rod, what is a coolant. So you have a lot of terminologies there. there. So again, some important terms here. So normally they used enriched uranium-235 or plutonium. These are what we used. This is important moderator. Now, for a reaction to proceed, right, it should be a slow moving neutron. Only slow moving neutrons are absorbed by the uranium. Because if the neutron goes very fast, it will just pass through the nucleus. But the problem, the neutrons which are emitted, right, they have very high kinetic energy. So after the first fission, the 3 neutrons which are coming out, they have very high kinetic energy. They can't be used for the fusion directly. So we need to slow them down. So we slow them down by using the moderator. These are slowed down by collisions with the moderator. Then you should know what is a moderator. So basically we fill up the entire reactor inside with a moderator, which is generally heavy water, which is D2O. Heavy water is D2O. Instead of H2O, we use deuterium, right? Or graphite or beryllium oxide. Again, these properties are very important. You should remember them. There have been questions based on this. Heavy water is the best moderator. So moderator should have what? Low atomic mass, poor absorption of neutrons, good scattering property. The size of the moderator atom should be equal to the size of the neutron. Those are some properties there. Control rods, I told you, they will absorb the excess neutrons. Generally, they're made of cadmium and boron. Cadmium rods are the best. They're used to regulate the net rate of neutron production. Coolant is simply, whatever heat is produced inside the reactor, that heat is removed. That heat is used to produce the steam, and that steam is used to run the turbine. So if you actually think about this, a nuclear power plant is nothing but a thermal electric power plant. Instead of burning coal, we are using uranium to produce heat. So liquid sodium is the best coolant. There's all the theoretical questions. Normally CET may they do come. Even bits may I heard they do ask such questions. Papers are not released, but from whatever we know, from that memory-based papers, they do ask such questions. CET may though you will get it. Clear with this? So just make sure to go through all this theory there. Not that great, but you should know the terminologies. They'll simply say moderator and you'll have no clue what they're talking about. Clear with this? That's about nuclear fission. So that is when you break something big into small. Then with nuclear fusion, in this case, we take the smaller particles and combine them to get a larger nucleus. Again, not really that important. Not much is asked on this. This is just for an example. So only thing that you can remember here is the lighter nuclei will combine to form a heavier nucleus. This will generally occur at a temperature of 10 power 7 Kelvin. We are talking about a million and more. And generally, this is what happens inside the sun. Again, need not remember if they'll give you this reaction, but just for your idea there. Look at this. Two hydrogens will combine. You'll get two deuterons plus two positrons. Then the two deuterons will combine with one hydrogen and you'll get one He3 helium isotope. Then 3 He2 will combine and we'll get one helium and again two deuterons. This whole reaction will produce an energy of 26.7 MeV. This is what is happening in the sun. Hydrogens are becoming helium continuously. So that's your nuclear fusion. There's not much on nuclear fusion. Should just have an idea there. Nuclear fission, we have that reactor and explanation and all that stuff. And the last thing, this is another theoretical thing. This is called pair production. Remember I told you, mass can become energy, energy can become mass. So in some cases, when you take a very high energy gamma photon, and when it hits a heavy nucleus, it becomes into particles. So you get a positron and an electron. So a high energy gamma particle it is kind of little easy for mass to become energy, but energy becomes mass. This I read, you require 36 times more energy than actually required. It's more difficult for energy to become mass, but it becomes. Energy of gamma photon becomes electron and positron. This is called pair production because you're producing the antimatter and the matter with the energy. The reverse of this is pair annihilation. Again, the terminologies are important. They'll use these words, pair production, pair annihilation. And questions will be pretty easy and straightforward, but because you don't know the terminology, you'll be gone. So this is called pair annihilation. In this case, you actually take a positron and an electron. When they combine, the mass becomes zero and you get pure energy. So if you take matter and antimatter, you get energy. If you take high energy for photons and hit with the nucleus, you get particles. Pair production, pair annihilation. Clear with us? The last 5-10 pages is completely theoretical, so make sure to go through them. That would be the end of the chapter also. So with that, we are done with modern physics, and that's our last advanced chapter. So next week when we catch up, we will be starting off with semiconductors on Tuesday. We'll catch up at 6 o'clock only. We'll be just taking 2 hours only. Those things are lot of theory again. You can see there's a lot of theory. The rest of the chapters will be like that only. I think all the chapters combined, I think we will have another at least 30 formulas you have to remember.